The next thing we want to do is talk about the matrix equations. So kindly recall, I made a remark in one of the earlier sessions that when you want to solve an ODE or a PDE, ultimately you would have to solve an equation something like Ax equal to b, a system of algebraic linear equations. So now we want to go from the Galerkin form to actually a system of algebraic equations. So let us set it up. Let the space Vh consist of all linear combinations of given functions denoted by NA, and these are defined on the closed interval omega bar. These are all real valued functions, and A goes from 1 to all the way to n. So in some sense I am being given a basis. Okay, so these are functions, NAs are the basis functions, and I am saying that using linear combination of these small n functions, they are small n in number, I can now construct a space Vh which still consists of infinite number of functions, but they are all linear combinations of these NAs. So it is like I am saying that I will take two unit vectors I and j, and linear combinations of this forms the R2 space. Okay, so I am just taking the basis. So in that sense, if I talk about a function space, I could possibly say there are some piecewise linear functions, and we'll look at them as an example, and then their linear combinations would give me all the members of this set Vh. So I could write that essentially if I want to represent Wh, a function, so let me say this Wh is a function of x, then this would be given as a linear combination of A going from 1 to n Ca times Na x, where Ca's are constants. So essentially I am saying that Wh x is actually given as C1 n1x plus C2 n2x plus C3 n3x plus all the way to Cn n nx. So you are giving me these basis functions n1, n2, n3, nn, they are given to me, and by constructing linear combinations of that I could generate an infinite number of Wh. Okay. You see, C's are all arbitrary. So note C1, C2, C3, Cn can have infinite combinations. So in that sense I have an infinite number of functions Wh. We will call NAs by a certain name. So we will call them as basis functions, because they are indeed the basis for the space. We can also call them as the finite element functions, because we will use them to do finite element analysis, and they are the basic functions. Sometimes they are also known as interpolation functions. all these are acceptable names. So, we have talked about representing WH of x as summation a going from 1 to n Ca Na of x. Let me remind you what the space was, the Vh. So, Vh consists of these functions Wh such that Wh are H1 and there is an additional condition that Wh at 1 is 0. Okay. So, as we said, NAs are supposed to be the basis function and n corresponds to the dimension of the space. For example, if I look at R2, the two-dimensional real space, then there would be only two basis vectors, and those basis vectors would be essentially the one along the x axis and the one along y axis. Of course, we could find other bases also. In that sense, the basis is not unique. We also need to have WH1 equal to 0. Okay, that's a requirement of the space, and you can see that this would imply that my functions Na at 1 should be 0 for all a going from 1 to n. Okay. So, no matter what functions I choose, they should all vanish at x equal to 1, simply because that is the requirement of this function space. Of course, you also have to keep in mind that they form a basis, so they should form a complete set. How about SH? So, we now look for members of SH, and for that we will need the function GH. So, need GH. So, the proposal is we will introduce an additional function which we will call n plus 1 x. So far I have small n number of basis functions. I will introduce another function, and this is such that at x equal to 1 it actually has a value of 1. Unlike the other basis functions which vanish at x equal to 1, this one achieves a value 1. And now I am going to propose that GH is given as G times n plus 1, and you can see that GH at x equal to 1 would be given as G times n plus 1 at 1, which is actually equal to G. So, this will suit my purpose, and then I can say that UH is VH plus GH, but VH is given as summation b going from 1 to n dB NB. I have just chosen a different counter. So, for W I use the counter A. It is just a counter, I mean I could replace this A with P, Q, anything. And just to be different, for this VH, which is the unknown, I am choosing the counter B, and the constants here were CA, and now I am choosing the constants dBs. Okay. So, I should now be able to construct the solution because I have now a representation for GH. And what you will notice is that if I look at UH at x equal to 1, this is VH at 1 plus GH at 1 This quantity is 0 because I am forcing all my NAs to go to 0 at x equal to 1. So, their linear combination would also be 0. So, this would be 0 plus G, which is actually equal to G. Okay. Now, what I can do is choosing this definition of W, and by choosing this definition of U, I can substitute in the Galerkin form and then simplify it further. So, let us do that. So, let me rewrite for you. WH is given as summation A goes from 1 to n CA and A. My VH is given as summation B goes from 1 to n dB and B. And therefore, if I write my GH as G times Nn plus 1, then I could write UH as VH plus GH, which is given as summation B goes from 1 to n dB and B plus G times Nn plus 1. If I use dn plus 1 as G, then I can write UH as simply summation B goes from 1 to n plus 1 dB and B, with the understanding that n plus 1 is a little bit different than the other basis functions, because it has a value 1 at x equal to 1, unlike the other shape functions, and the d n plus 1 has a value G. So, it is a known quantity. So, I am going to now use this and plug it into my Galerkin form. So, let us recall the statement of Galerkin form. It was given as A of VH, sorry, WH, VH. This was WH comma F plus WH 0 times H minus A of WH GH, and this has to be satisfied for all WH that belong to the space VH. Okay, so, this was in essence the statement of the Galerkin form. So, we derived the strong form, the weak form, then the approximation, which is the Galerkin form, and what this is saying is that W is your test function or the weight function, and this statement has to be satisfied for all W's that belong to V. Now, you can ask yourself, how can I take care of all W's, because NAs are given to you. So, all W's would imply all arbitrary combinations of CAs, which would actually imply it should be satisfied for any arbitrary value of C. Okay. So, that is how you would have to test this function and generate your equations. So, let us do that. So, we will substitute in this for WH and for VH. So, this is what we get. So, let me write this down. So, A of, so WH is given as summation A goes from 1 to n CA and A. Okay. That is this first statement. For VH, I am going to write summation B goes from 1 to n dB and B. So, that is the first term. The second term is going to be given as summation A goes from 1 to n, and for WH I would write CA and these NAs comma my F. So let me put the big bracket. Right. Now I am going to talk about the next term, which is WH0. So this I am going to write as summation A going from 1 to n, and WH is CA, but now my NAs have to be evaluated at 0, and this times the H. Okay. Then the last term, which is minus A of, and I would put in here summation of A going from 1 to n, CA NA, comma, GH is given as G times n plus 1. Right. And this statement should be satisfied for all CAs, because the Galerkin statement was to be satisfied for all WH, and the only way the WH can be arbitrary, as we argued, is your basis functions are given to you, so CAs are arbitrary. So therefore, this statement should be satisfied for all values of CAs. Okay? And of course, those are infinite values. You can fix all C1 through Cnn minus 1 and just vary infinite values of Cn, and then likewise you could fix the other values and change one of them. Excuse me. Now we will use the bilinearity of these operators.